videos. I don't know what we're going to call these videos yet. I think I've got one other one that's similar setup. It's about the Great Pyramid on the Giza Plateau, and we talk about sacred geometry involved in that and the ratios and how it describes the circumference of the Earth and the dimensions of the Earth and the Moon. Now, what I want to talk today about is the circumference of the Earth again, but in a later period, around 275 BC, this Greek polymathematician lived in Alexandria on the coast of Egypt. That was during the reign of the Ptolemy rulers, the Greek rulers in ancient Egypt. You're probably familiar with Cleopatra. It's Cleopatra number 7. Not many people know that there were 7 Cleopatras. But anyway, she's the one that we associate with when we think of Cleopatra. And that was the end of the pharaonic period in Egypt. So we'll just get back to Eratosthenes, the Greek polymath. And what he's probably most known for is working out the circumference of the Earth, which was a pretty mean feat in those days, 2.2 thousand years ago. Oops, I'm going to grab hold of that thing. Anyway, so I think he was a bit of a mate with Archimedes as well, because they lived around the same time, and I think they used to exchange a bit of info with each other. So now, as the story goes, Eratosthenes was given some information about a town in near Aswan of Alexandria, and he was told by some very astute village people there that on the summer solstice in June in the northern hemisphere, there was a water well. It was quite a deep dug water well, and he was told that again on the summer solstice the sun would reflect at the base of the well. Now this would create no shadows on the wall of the well. And he thought about this for a minute, and he realised that, well, that would mean that the sun was directly overhead. Not just overhead, not above us, but directly overhead. So that got him thinking. And what he realised also then was that if he poked a stick in the ground, a perpendicular stick in the ground at Alexandria at exactly the same time, well, that would create a shadow. Now, he'd already in the past contemplated that the Earth was a sphere or round, and this was something that sort of helped him confirm that belief. And he was he wasn't the first to come up with the idea of that either. The very, very ancient Egyptians knew that, and that's very obvious because of the construction and a lot of things that evidence in ancient Egypt, probably thousands of years before Eratosthenes, Pythagoras even. And Pythagoras had floated this idea that the Earth was round about 300 years before Eratosthenes. So let's get into this now. How did he work this out with a couple of like a shadow, a stick, and the sun? And well, let's have a look. We have this dome here, and it represents the Earth. Alright, now let's say this this block here represents the well. That would be the surface of the earth. Where's my pointing thing? There it is. So if that's the horizon of the earth, or the boundary of the earth's surface, then this would be the well. It's obviously not to scale, but it's going down into the earth. Now what we're going to do, we're going to put a stick in the ground. I'm just going to find a stick. I'll just have to find a stick, folks. I'll just go outside for a minute. No, I won't actually go outside. What I'll do is use a little bit of cardboard and put a stick over here. Righto. Now, you sort of wonder, why did I put that at an angle? Well, I actually didn't put it at an angle in comparison to the Earth's surface, because the Earth's surface is, here we go. So this is pointing down to the center of the Earth, the well is pointing down to the center of the Earth, and so is the stick. So, you know, if that was the center of the Earth there, let's say, that point. Now, well, if we call this just S, and we'll call that A for Alexandria and Cyan. Okay. So it turns out that Cyan is right on the Tropic of Cancer, and on the solstice, the summer solstice, the sun is directly overhead at midday, and there we go. That's why we had this shadow that reflected at the base of the well. So we had this shadow that reflected at the base of the well. Now, let's have a look at the sun. Yeah, I've already put a little sun in there. So obviously the sun's a lot further away from the Earth than on this representation here, but it doesn't matter, it's because it's not going to fit on my page. But anyway, now the sun obviously sends out light in all directions. But because it's so far away, a certain amount of those rays will hit the Earth perfectly parallel. So we'll draw a couple of lines in here and we'll just represent that a little bit, and we'll draw, let's draw some sun rays going out here. There you go. And draw some more over here, maybe. It's just giving you an idea of what's going to happen. So now there's obviously rays coming out of the sun in every direction. Now there's a certain amount of rays that are going to come and hit the Earth directly. Let's draw 3 in, because I think 3 looks nice, that's all. It's the only reason. Alright, so these rays are all hitting the Earth directly and perpendicular or parallel, or however we want to describe it. So therefore, if the further we get around the sun here, obviously those light rays are going to start moving out. And then if the sun is not directly overhead, some of these light rays are going to hit that well, and then what's going to happen is it's going to cause a shadow across the side of the well. So this is how we know that the sun is directly overhead. Anyway, so let's get to our shadow in Alexandria. So what he noticed was, here we go, I better draw some lines in here. So some of these rays were pointing at the stick, because in Alexandria the sun wasn't perfectly overhead. And that's due to the distance between Alexandria and Cyan. Let's put that back where it came from. So what I'm going to do, I'm going to draw in a shadow line here. There you go, there's a shadow line. Excuse me. Now we move ahead a little bit before we get into some calculations. Eratosthenes apparently hired a guy to pace out the distance between Alexandria and Cyan. He may have done that, but you know, he may have done it just to prove it, but I think also that information would have already been at hand with the trade routes and things like that. So anyway, so maybe if you had to prove the fact because he was doing a scientific experiment, okay. He hired this guy, and this fella walked it out, and he must have counted his steps. Can you believe it? He worked it out at 5,000 stadia, and that was the unit of measurement at the time. Now the stadia is around about 185 meters. So when we break that down and translate it to a metric, what we came up with is what was it? 890. Yeah, I got my notes over there. I've got so many numbers. All right, so the distance was 890 kilometers. Okay. km. Right. So now he's got a fair amount of information. What we need to do, and what I'd like to do on this video, is explain how he came up with the circumference of the Earth with having this information, all of these at his hand. So just have to say this: he wouldn't have just poked a stick in the ground, right? Because if you could see that shadow, actually that's not a great shadow to work with because it's too long a stick. But anyway, this shadow, if I move it, you can see the shadow moves. So for the experiment to work, he would have had to have that stick absolutely perpendicular to the ground. Therefore, he would have had to have a perfectly level surface to work on, and that wouldn't have been terribly hard. He probably he could have created a round pad or a square pad on the ground. He would have leveled it off. He may have dug some channels in the ground, a grid pattern of channels, filled them with water, marked off where the level of the water was, and then proceeded to level the ground to that point of where the level of the water. That would have given him a level surface to work with. Then he would have apparently poked a stick in the ground. Now again, if that stick was not perpendicular perfectly at right angles with the base, it would give him a false reading. So anyway, I made up this little prop, which is a similar sort of thing to what the ancient Egyptians would have used as a levelling device. And it's something like a plumb bob, really. If we can see that very well. I hope we can. So this would have been calibrated on a level surface, and the calibration line, I've put a timber in there with the two corner points as my calibration lines. So now, if I move the square off angle, it's not going to cross the calibration lines. As I bring it down, there you go, you can see that's how that works. So then this line here would be perfectly plumb, and then he would have used something like that to place his stick into the ground. Now he also would have had to know the exact measurement of his stick from the ground to the end of the stick. He also needed to measure the shadow line here. So he had the height of the stick and he had the shadow line. So then what he's been able to do is work with a bit of Pythagoras theorem. So we've got a right angle triangle. So if he's worked with Pythagoras, now what he's going to be able to do, because he's got a right angle, we all know what that angle is. It's 90 degrees. Now let's say this represents now, this little sketch represents his stick and his shadow. What I've been able to do with the bit of information that Eratosthenes left us was, and we're quite fortunate with this, because he left us the information about the angle that he discovered at this point going through here, which would be the hypotenuse of a triangle. If we draw that line through there, we draw that line, we're going to call that the hypotenuse. We're not here today to work out what the length of the hypotenuse is. What we want to know is what this angle here is. What we actually want to know is how he got that angle there, because we know what the angle is, and he gave us the information that that angle is 7.2 degrees. Now the other thing I'd like to say is that he probably wouldn't have used typical Greek measurements either, because as far as I know, the smallest unit of measurement was about 19 millimeters, and it's based on the thickness of your finger. But the Egyptian cubit rod, which measured around about, depending on the period, 440 millimeters, and the smallest measurement, increment of measurement on a cubit rod is roughly about 1.5 millimeters. Now here's a picture of one now. And I've drawn in the some measurements where blah blah blah. Alright, we're back to working out this problem here. Now I'm not going to do it here because it's probably going to take too long, but what I was able to do was reverse the math, because Eratosthenes gave me 7.2 degrees. I was able to reverse the math, and I could work out the length of the shadow. And what I've done is given the stick a value. Now I could have given it any value really, but I've given the stick a value of 50 millimeters. Right. Now, without doing the math on the page here, I came up with a shadow length of 6.27 millimeters. So that's pretty much what the information would have been if Eratosthenes had these measurements. Now his stick could have been 2 foot long, you know, who knows. But what this boils down to is a ratio of 6.9. So that's the ratio. Now I've worked that out earlier too, but don't worry about that. What we want to know, this is the exciting bit coming up right now. Here we go. Because I've searched YouTube high and low, I've searched the net high and low, looking for tangent, a formula right to find tangent. No, forget it. There's none there. Everyone says pull out your scientific calculator. You know, so I wasn't satisfied with that. I wanted to work it out. I wanted to know how Eratosthenes did this. Righto. Now he's got that information. Let's transpose this information to a drawing. This drawing, so he's drawn a circle. Now, with the benefit of being a friend of Archimedes, he knew how to work out the circumference of a circle. Now, you know, that was very fortunate, because that's what Archimedes did. Archimedes is responsible for pi. And now, if you don't know what pi is a ratio of the circumference of a circle. And we use it. It's what we call a mathematical constant, I believe. And we use it for finding the area or the circumference of a circle, and lots of other applications. Anyway, now, shadows everywhere. We're talking about shadows, and I've got them everywhere. I'll try and do this. Righto. So now this radius, let's say this radius represents the stick. So this radius will be 50 millimeters. Now, 50. Let's draw in this shadow line. So this shadow line, in all reality, that's the point there. Because this point here, that's what I'm going to draw, is this point here on the circle. So it'll be quite an acute angle at 7.2 degrees. You'll probably have to admit. Let's just draw it in. If my pen won't, please work, pen, please. Okay. So I hope you can see that. What we also know is that on the circumference of a circle, there are 360 degree points. What we also know, with the benefit of Archimedes, is that pi. This is my fun bit now. Okay. So what we know is that pi equals 3.14. Now that's a ratio, or it could also be translated as 22 over 7. So let's work with 3.14. Now, because Archimedes is a clever chap, he worked out that the circumference of the circle, and we'll write that here. See, what have we got over here? Nope, we won't have that. Okay, so we know that C equals pi r2. The circumference of a circle equals 3.14 times 2 times radius. Alright, so break that down really quick and easy. That's 3.14 times 100, because the radius is 50, Alright, let's just write it down like that anyway, just so we'll keep it all clean and mathematical. Not that I'm overly mathematical. 3.14 times, which is now the diameter, right? The diameter being twice the radius. So now, the circumference of this circle, right, not all circles, just this one, the circumference of this circle is pretty simple, times blah blah blah, equals 314. That's pretty cool. That's pretty cool. That's easy. Alright, that's easy. What we want to know is what's the we're working our way to finding this 7.2. So now we need to know what this measurement is across here. We know what it is in cyan, but what we need to know is what actually is so what we want to know is what is 1 degree worth, the value of 1 degree. So 1 degree should equal 314 divided by the 360 points of a circle, divided by, and that, let's write it here, because so there, now that works out to 0.872. So what we've got now is we've got the length 8.72 millimeters, the length of 1 degree on this circle. That's pretty cool. Now, to find the angle that we need here, all we have to do is divide the shadow length by 8.12 degrees. So now, how are we going to do that? We'll call it shadow length. SHL, that'll do, equals, what is it? What am I doing? Yeah, the shadow length equals, yeah, there it is, 6.27 divided by, now he's got this angle, the 7.19, 7.2 degrees. He needs to work out what the multiple is. Let's have a look here. Let's have a look here. Let's have a look here. Yes, okay. So, what he did, because he knew again, he was loaded with information, he knew that there was 360 points on a circle, 360 degrees. So he's taken the 360 degrees, divided it by 7.2, which he found up there, by doing this, by doing that, and he's come up with 360 divided by 7.2 is 50. So now if he multiplies the distance, remember he got that guy to walk from Alexandria to Cyan, and he came back with 5,000 stadia, and then I translated it to 890 kilometres. Well, now, so 7.2 multiplied by 50 is 360 degrees of a circle, the Earth, which when you multiply that together is 444,500 kilometres, and that's pretty close to what he came up with, the measurement he came up with. The actual circumference of the Earth is 40,030, which means it was only really about 10% off his calculations. So, you know, not too bad for a stick and a shadow and a well I reckon that's pretty good stuff. Oh yeah, one more thing. There he is. The old dude. Yeah, pretty cool dude. I wonder if anything had to do with the size of his head, that he wanted to work out how big the Earth was. Maybe, you know what, I reckon he's got an equation for the ratio between the size of his head and the size of the Earth. It's got to have a pretty big brain in there. So this was all pretty good. That worked. Are you guys happy? I'm happy. I'm happy because that worked. See you on the next one. What's that? Whatever that's going to be. I might get inspired to make another video. Ring I made once. Yeah. See you later, guys.